piecewise splines are, I think, very, very useful because you can't just sit doing what I did here, which is take trajectories and then find the constants. We need a method which is more generalizable. So this last part, and I'll cover this briefly, we will not go to the math of figuring out the constants because Python is a package which will do it for you. So what is piecewise splines? This is a very general way of doing things. So if you have, let's say, some points, so you can give any number of points. I just chose 4 points. What this will do is it will fit a third order polynomial always. So let's call that, say, Q1, Q2, Q3. So Q1, Q2, Q3 are third order polynomials. So why use third order? Now, most times you want that curve to pass through 2 points, right? The start and end. You also want to ensure some kind of continuity where it passes. So it turns out that if you have third order, it's sort of, well, third order equation has 4 constants. So it gives you, it fits 2 points, the first, and it basically fits the start and end points, but it also gives you 2 free parameters. Those 2 free parameters can be used to ensure that the velocity here is continuous and the acceleration is continuous. So you normally don't go beyond acceleration. So if you think that you like the solution where the acceleration is continuous, then piecewise polynomial is for you. I'll go a little bit into the details of how these curves are generated because it's kind of not very obvious. How can you fit, if you're given 2 points, you want to fit a straight line, but how do you go about fitting cubic polynomials? I'll go to the details, but we'll eventually use some code which will do it for us. It not only does that, not only gives you the position profile, but also gives you the velocity and acceleration as I'll show you in the code. So let's say that we are given data points. Like so, let's say that this is T0, T1, T2, T3, and this is Q. So what you're given here is T0, Q0, T1, Q1, T2, Q2, T3, Q3. Let me change my, this is not a good way. Well, let's just, I need, these are, this is not right. These are just the curves. So I need to give some values to this. Let's say, what should we call it? Let's call it theta 0, theta 1, theta 2, theta 3. So we're given theta 0. So these are numeric values. And the Qs are actually supposed to be the splines. So they are not specific values, but they're curves. So they are third order polynomials. Okay, so we can just keep going like this. Let's say that we end at Tn theta n. Okay, so what we have here is n plus 1 data points. Why n plus 1 is because we start at 0 and go all the way to n. So there are n plus 1 because of the 0. Our goal is to fit a third order polynomial through these various points. Okay, so this is what we'll do. Assume a third order polynomial. Let's call that Qi. And let's call that, let's say that it is AI0 plus AI1. Now, what we'll do here is instead of specifying it as t plus so on, we'll just make it like this, t minus ti plus ai to okay, the specific choice is going to help us save us with one constant, as you see. When I put, so when this will obviously make this pass through the points q1, well, in this case, theta 0, theta I, and theta I plus 1. So you'll see that when you put t equals ti, all the terms except the first one will cancel, so it makes it easy to eliminate some of the constants. So this is what we assume for each segment. So remember here, there's q1, q2, so on till qn. Okay, now let me just walk through the fundamentals of the number of constants which will come from this, how this is set up. We'll not set it up, but I'll just give you the idea of how this is, how actually go about finding these constants. So here is what is done. Let's say that we take one more. So these are the points. Let's call that ti minus 1, ti, ti plus 1, ti plus 2, and we fit qi minus 1, qi, and qi plus 1. And then I told that qi, which I'll take from the previous page, this equation. Okay, we are all ready to start exploring this now. So now we have these equation, we have these points. So what we do here is we know that this will pass through qi. So you can see qi, it passes through ti, right? So you put t equals ti, which means that when you put this here, this term, this term, this term cancels off with 0, you get ai 0. So by assuming this form, you basically eliminated 3 of these constants, then you put t equals ti. But this also passes through ti plus 1. So qi ti plus 1, which is this point, we'll have ai 0, ti plus 1 minus ti, sorry, ai 1 plus, we continue it on the next line. Okay, so it passes through those 2 points. And as I said, I'm just going to focus on this part. Okay, so so we got 2 of the 4 constants. We still need to evaluate 2 more constants. So what we'll do is we'll ensure that it is actually continuous at this point. The first and the second derivative is continuous. So for that, what we set up is qi at ti equals qi at ti plus 1. This is the first derivative. Sorry, so qi, hold on, qi ti, so this is going to be this point derivative should be equal to qi minus 1. Sorry, it's p I minus 1. So this for this point at this, so ti. So this is ensuring that at this point the derivative, first derivative is continuous. Similarly, we set up the second derivative to be continuous. We can do the same thing for I plus 1. So it will be qi ti plus 1. So this is this point. Velocity there equals q, the derivative evaluated at I plus 1 using the I plus 1th. So it'll be first derivative at ti plus 1, and we do the same thing with the second derivative. The number of constants and number of conditions. And to determine the number of constants, I need to ensure that the constant is equal to the number of conditions. Okay, so we have n plus 1 points. Okay, 0, 1, 2, so on till n. We'll have equation 1 here, equation 2 here, q3, and so on. So the last point, these two, we'll have qn, right? So you can just see the logic. It's q1 and 1, q2 and 2, so qn, n. So that should be, so n third order polynomials. So since we have a third order polynomial, we have 4 constants for each polynomial. So 4 constants for every third order polynomial, which means that the number of constants is simply 4 times n. Okay, so we have to pretty much set 4n equations to solve for the 4n constants. So how do we do that? So I have given you some indication as to how it is done. It's basically these things, but now we're just going to, I'm going to take this and basically count these equations. Okay, how do you count them? So here's how I would count them. Okay, so what we did was, just take one segment. So let's say this point, this one. Okay, so we specified the condition that the position is given to us. So here let's call that theta 0, theta 1, theta 2. So we know the values at, so we know the okay, so we know the values at this point and this point, right? So so since we know the value at this point and this point, we can keep doing that till we reach, let's put this will be theta n and theta n minus 1. So we'll deal with the end points slightly differently. So let's deal with these points in the end. Okay, let's not worry about them. Let's just look at the points in between. Okay, because it's the end point becomes slightly confusing. So let's look at all the intermediate points. So if you have the intermediate points, so each, so we have n minus 1 intermediate points, right? I removed 0 and n, so I'll be left with n minus 1 points. each of those points, I specify two conditions. One is this point, the value is known, this point value is known. So I can specify two n minus 1 position conditions. That is, the position is specified. The second thing I can do is for each point, like this one, I know that the velocity should be continuous. So I'll take this segment, put the value here, the velocity at here, and then take this segment velocity again at that point, and that should be continuous. So that would be equivalent to this condition here. This is the velocity condition, right? So I'll get this for each intermediate point. Since there are n minus 1 points, I'll have n minus 1 velocity conditions. Okay, next, we also have a similar thing for acceleration. So again, at this point, acceleration should be continuous. Acceleration should be continuous. If you go back here, that condition was here, acceleration. So we have here n minus 1 acceleration conditions. Okay, now one thing I'm missing though, so let's see if I've covered everything. So I've covered, uh, this is the same as the position, velocity condition, acceleration condition, position condition. So I've taken care of all this except for two, which I just ignored, right? Earlier I said, let me just do this in a special way because there is no segment to this fellow's left and this fellow's right. So we also know the value at theta 0 for q1 at 0 and qn at n. So that gives us two conditions and positions. So two conditions on theta 0 and theta n. So that is q1 at 0 is known and qn at n is known. Okay, so I think that's all we can get from here. So we just sum this up. So we have 2 n minus 1 plus n minus 1 plus n minus 1 plus 2. So that will be 2n minus 2 plus n minus 1 plus n minus 1 plus 2. I think we can get that off. Okay, so we're left with 2n minus 2. Sorry, 4n minus 2. Right? 2n plus n is 4n. Okay. So here's the thing. We have 4n minus 2 conditions and 4n constants. So we are short by two conditions. We need to specify two more conditions, and then we can completely determine this equation. Basically be setting up like a matrix, a big A matrix, but you don't have to do it. Python will do it for you. So two conditions are missing, and this is where you get some freedom. You can choose whatever you want for those two conditions. So let's me write that down, and then I'll tell you what those conditions usually are. So we have 4n minus 2. So we have 4n constants is greater than 4n minus 2 conditions or equations. We need to choose two more conditions or equations to compute all 4n constants. Okay, this is where you get some of these cases. So here are few ways of imposing the two conditions. Okay, and I'll show you why these conditions actually, they will be a big deal when you look at the kind of velocity acceleration you get based on what you specify. So there are the following ways people use it. One is known as the natural spline. Okay, what the natural spline does is you impose this condition f double dash at t0, that is the acceleration is 0 and acceleration at the end is 0. Okay, so the first and last point acceleration is 0. It's totally arbitrary. You don't have to, it's not necessary, but it's good because if you have a motor and it's trying to not accelerate it suddenly at t equals 0, that'd be good. And you stop it at 0, this is something good for the motors. There's something called the clamped condition, which says that you look at the first derivative at x0 is 0, and the first derivative at tn is 0. Okay, and then the third one, it's called not not condition. It basically ensures that it's kind of weird. It says that the third derivative at a third derivative, uh, just move it to the next page. This one is a bit odd. Let me draw figures. This one does the following. Um, let's draw these, and then we have okay, and then we call this Q1, we call this Q2. So those are the polynomials Q1 and Q2, and this was T0, T1, T2. Okay, so the last one is Q1, the third derivative at T1 equals third derivative at T1. So you take the polynomial Q1 and take the third derivative, compute its value at T1, and take the third derivative of Q2, and then compute value at T1, and set that equal to each other. So what this means is that if you take remember Qi is something like AI0 plus AI t minus Ti plus AI1, AI2, t minus Ti square plus AI3. So if you take the third derivative, this will become third derivative of this is 0, third derivative of this is 0, third derivative of that is also 0. So you'll only be left with this. So the third derivative of this is 3 times 2 times AI3, I think. 3. Will it be a constant? No. So let's do it. 3 AI3 t minus t square 6 AI2 t. So first, second, 6 AI2. Yeah, it'll be a constant. 6 AI3. So what this is saying, this condition is saying is that six A13 is 623. So you just basically equate the two. And then this is just one of the two, right? We need two conditions. The second condition is based on the last point. So we have last three, we have uh, tn, tn minus 1. Let's join them, un, un minus 1. So we'll say that qn, third derivative at t n minus 1 is q n minus 1, the previous segment, third derivative at t n minus 1. So that's the second one. Okay, so the question is, why is it called not a knot? Uh, uh, so if the third derivative is like so, I don't know, to think about it, why it's called a not a knot. I think it suggests that somehow that knot really disappears. It's not really a knot point. I don't know. Okay, so those are the three ways in which you can specify those two conditions. And you'll see that those two conditions give you very, very different trajectories, especially for the first and second derivative. So here is the three ways. You can set up equations, but I wouldn't recommend setting up the equations yourself. We just surrender to these things to Python. So there is in SciPy interpolate, there is cubic spline. Here I just randomly gave data x 1, 2, 3, 4. Think of x as time. Y is your angle, 3, 6, 5, 8, some random data points. Here is how to generate the cubic spline with not a knot, clamped, natural. Natural is also, yeah, the first one where the derivative was 0. Okay, now here's the best part about this. It's actually better than MATLAB. This one actually gives you, well, these are the breakpoints, are the points where we have those knot points, but then it actually lets you compute the first derivative. So there's a structure which comes out of this CS. That CS structure, you can call it anything you want, just call it CS. This actually gives you the first derivative and the second derivative. Super nice. You really don't have to spend any time doing it, because you can use this in, let's say, trajectory generation. We need the first, second derivative. So you get that. What I've attempted to do here is show you the data as O's, show you what the spline looks like. That's the position curve. Then I took the first derivative and the second derivative, and I think they will come with, I think the legend will make it clear. So let's just run this. This is for the natural spline. Okay, so blue is the data. Cubic spline is in orange. Okay, so it passes through all the data points. So on all cases it will pass through data points. However, look at first and second derivative. The first derivative, let's look at the second derivative first. The second derivative, we know that the natural spline makes the initial position, initial acceleration, final acceleration as 0, which it does. And the consequence of this is that you can see that the acceleration is well, it's negative, positive, negative. Velocity goes from, it actually jumps from 0 all the way to 4, and then shows this nice smooth curve. But again, when it's here, it jumps from whatever it is, little above 4 to 0. So it's not good for velocity, but the acceleration is smooth. Okay, there's a kink here, which means that the derivative of acceleration, the jerk, won't be continuous. Okay, so that's what you'll get if you use natural spline. Let's change the condition to clamped. Clamped is when the velocity at the endpoints are 0 versus the first one, which the acceleration was 0. Okay, so here is what you get. The orange is clearly, it passes through all the data points. Velocity starts at 0, ends at 0, nice thing. But look at the acceleration. It jumps from 0 to 15. Terrible for the motors. Goes negative, positive, negative. Eventually, it comes to a rest. Okay, so achieves the same objective of taking the points through the orange, but then it has a very different acceleration. It just means different things for a motor. Also, the energy usage will be different if you have different profiles. One of them might be more efficient than the other one. That's something you need to check based on your power dissipation in the specific motor. You might have a hydraulic system in which the power consumption will be different from an electric motor. And then here is the not or not, the third derivative as the second point should be equal, is continuous. So here is probably what we've been accustomed to. The acceleration, you can see it goes negative to positive, doesn't go back and forth. The velocity is, velocity jumps, will actually also acceleration jumps. So it's not really good news for the velocity and acceleration, though the position looks like this. Okay, so